Hi, I'm Brittney FANG. I'm a third-year mechanical engineering student at the University of Texas at Austin, and this is my final presentation for my project, Machine Learning Optimization for Multifunctional Material Design. This summer, my project objective is to develop a machine learning model to optimize material design analysis using spiders. So what is spiders? Well, SPIDER stands for Spatial Interpretation for the Development of Reconfigurable Structures, and it is a tool that generates adaptive graph-based structures using information produced by a modified Linden-Mayer system, or L system for short. A conventional L system is an algorithm that operates on a defined alphabet of characters according to a set of production rules. From an initial axiom of characters, you can recursively apply the production rules to produce a new sequence of characters, and you can continue to recursively apply the production rules to the output and end up with a much longer string of characters. And these characters in the L system string produced by spiders represents an operation to be performed on the graph of structural topology. The difference between the string produced by the conventional L system versus the spider's L system is that the spider's L system uses not only the alphabet, but also incorporates numeric parameter values. And these parameter values modify the function of the operations performed on the graph. For example, if A represented a move operation, then spiders would start here, and then the numbers associated would tell the spider where exactly to move. This is how spiders work step by step, but the key takeaway to understand is that a numeric array is inputted into the L system, and the L system spits out a long string that serves as instructions for spiders to create the graph of structural topology, and the created graph is sent to finite element analysis, or FEA, resulting in determined performance metrics for the structure. Now you know how spiders works, but why do these graphs matter? Well, spiders can be used to optimize multifunctional material designs. Multifunctional meaning that the satisfaction of various design objectives, for example, stiffness, mass, or conductivity, can be tested with these generated graphs. So if a material design called for a structure to meet certain criteria, spiders can generate these graphs with various materials and shapes to be analyzed by FEA, determining what type of structure is needed to meet these design objectives. Now, how does machine learning fit into all this? Well, it is currently inefficient and expensive to conduct large number of FEA calculations needed to quantify performance of these structures. So the goal is to integrate machine learning to replace FEA by mapping information from the spiders framework directly to the performance metrics. The tools used to develop all the machine learning models are Python and machine learning backend packages including TensorFlow, Keras, and scikit-learn. The plots for visual analysis are created using matplotlib. In the upcoming slides, the models you'll see were all constructed according to a regression problem. So a little digression. Coming into OREU this summer, I had zero experience with machine learning, and the biggest question I had before I started was how exactly do you teach a machine to learn something? I'm still no expert, but after much researching and watching informative YouTube videos, I have a pretty good grasp of the main idea. So how does it work? Well, a basic explanation is that structures called artificial neural networks are the means of machine learning, and they're built on a set of algorithms. A neural network can consist of multiple layers of units called neurons, which are linked together by various weights, and these weights represent the strength of the connection between neurons. For example, if the weight between neuron 1A and neuron 2 is in much greater magnitude than the weight from 1B to neuron 2, then that means neuron 1A has a much greater influence on the value of neuron 2. These types of relationships ultimately affect the values of all neurons, from the input layer to succeeding layers to the final layer where it spits out final values. The essence of training a neural network to spit out certain final values from an input is an algorithm called backpropagation, which essentially teaches the model how to recognize how far off it is and improve itself to work according to how a user wants it to. This is a very simplified explanation, so if you desire a more detailed explanation, I suggest watching the video series I've linked. But for purposes of understanding my project, you can think of machine learning using neural networks as inputting info from previously collected data into a structure that can be trained to recognize patterns and output a prediction. Before I came in, there was a first training attempt using the initial array from step 1. The findings are that the trained models were pretty good in predicting the stiffness and mass of these structures. Ideally, the points would lie along the exact prediction line, this blue line you see here, but the majority of the points are still within 2 standard deviations within these black lines. Significant outliers do exist, which is a major issue because the model predicts artificially good and bad performance. For example, really high stiffness, when in reality it should be a lot lower. So this is where I come in. My mentors wanted to see whether this model could be improved so that the outliers are eliminated and ideally all predictions lie along the blue line. I decided on training a model using the L system output string from step 4 instead because I hypothesized that it takes into account more information that can be used to find a better pattern. Here are the results for predicting stiffness training with the initial genome array versus the L system string. Taking a quick look between both models, the L system string models are much narrower, with the points within 2 standard deviations lying a lot closer to the ideal line. If you notice, there are also 2 vertical columns that contribute to most of the error, so I decided to train without the data at these points and ended up with the last model you see here, where the outliers are significantly reduced. Here's the results for maths, and there's not much improvement, in some case a little worse looking at the relative error. However, absolute error remains almost the same. So on average, predicting performance metrics improved quite dramatically training with the L system string. The error is much smaller. This reinforces the machine learning capability of replacing analyses such as FEA. However, the problem of outliers still remain despite being less extreme. After developing this model, I decided to determine possible connections between stiffness and mass, because for example, if stiffness is higher error when mass is a certain value, then those points can be easily disregarded as accurate predictions, and the model can still be used for majority predictions. After analysis, however, you can see in the plot that there is very little relationship or discernible pattern between some relative error and predicted values. There's a relatively even scatter of low to higher error at all predicted mass and stiffness values. For example, if you received a prediction of mass for 40, then there are red points, green, and blue points, which means that there's no telling whether the prediction that you got has higher or lower error. But to reiterate, on average, the L system string model predicts accurately, with even 10% some relative error not considered to be horrible for design. So my mentors have discussed the idea of using this model as a way to inform the first generation of designs, rather than starting off with 100 random designs of mass and stiffness, but using it as a filter to pick out on average accurate designs and disregard the bad ones. So this is a possible implementation of the L system string model I developed that can optimize multifunctional material design. After successfully developing a model using the L system string as input, the next step I decided to take was designing a machine learning model to recognize images of the spider's graphs from step 5 and ideally map directly to the performance metrics. Initially, I attempted to create a model that identified images of the spider's graphs and mapped them directly to a stiffness or mass value, basically like the L system string model, but instead of the L system string as input, the images would be used as input. This proved to be a way too ambitious project that did not get any good results, and we were cutting close on time. So I decided to develop a basic image classification model in which I trained the model to classify the images of the spider structures to a certain range of mass or stiffness values. For example, an image of a structure with a certain mass value could be classified as either light mass or moderate mass or heavy mass if there were 3 total classes. So how is the image recognition model different from the L system string model? Well, instead of a string of characters as input, the model breaks down input images into its pixel values, which is a lot more complicated considering image dimensions. The initial generated images of the spider's graphs were not ideal for training the model because they were too big with too much white space that would cause noise, making it harder to train. So I downsampled the images to a smaller size and cropped out the white space. I also changed the images from color to binary black and white images because colored pixels have 3 RGB values associated, whereas binary only has 1. So changing reduces the complexity of the info to train. When the image pixel values are processed by the model determines patterns, and instead of spitting out a single prediction, it spits out an array of probabilities that classifies a certain image to a certain label. For example, this array could be spit out by the model training to classify images to 4 different labels. In particular, this tells us that there's a 47% chance that the image belongs in label 1, which is the highest, so that the trained model would classify this image as in label 1. Here are the accuracy results for the model trained to classify spiders' graphs to 10 successive ranges, from least to highest mass or stiffness. Mass has high overall recall accuracy, probably because it is intuitively easier for machine learning to see that more lines means the heavier the structure is. For stiffness, it is less accurate, but because it is less intuitive to determine, the overall accuracy of almost 80% is pretty good. The results prove the ability to classify spiders' graphs directly to a certain range of mass or stiffness pretty accurately, emphasizing the versatility of machine learning to optimize multifunctional material design using spiders. I'd first like to thank the sponsors and the people who organized OREU this summer for giving me this opportunity. I have learned a lot in such a short time, and I hope to apply what I've gained here in future endeavors. And finally, to my mentors, Darren and Brent, thank you for being patient and welcoming in the beginning. It is certainly strange meeting and working closely just online, but I've had a great experience working with you all, and I look forward to in the future. And with that, I conclude my presentation.